Okay, welcome everyone to Water Quality in the Distribution System Workshop. You are in the right place if that's the webinar you're looking for. We're going to go ahead and get started at the top of the hour. In the meantime, if you're interested, it looks like we got people joining from all over. So I invite you to put where you are joining from in the chat. It is always fun to see where everybody is. Otherwise, we will start right away at the top of the hour. Thanks, everybody. Okay, welcome again, everyone. We're so glad you decided to join us today. Welcome back to those of you who have attended one of our webinars before, and if you are new, welcome. We're so glad that you are here. We are going to be exploring water quality in the distribution system as a workshop today, and my name is Lori Krings. I will be your moderator. So our plan for today, we'll just walk through briefly so you can kind of get a sense of some of the logistical things that we need to keep in mind. We are coming to you from the Center for Technology and Training here at Michigan Technological University in Houghton, Michigan. And we are excited to welcome back both Daryl Gotham and Greg Pearson with us today as our instructors. Greg is a water and wastewater trainer here at Michigan Tech, and Daryl is one of our research engineers, also from Michigan Tech. And we're really looking forward to what both of you have to share with us today. We also have Ingrid Sandberg here as our producer, keeping everything running smoothly in the background. So thank you, Ingrid. Just a few things for the housekeeping side of things today. There will be polls. So if you find that you cannot see the poll window when that pops up for selecting your answer, you could have pop-ups blocked in Zoom. And if that seems to be an issue that you can't quite remedy, you are welcome to put your answers into the chat. That's totally fine. And we do have closed captioning and accommodations available. If you need anything, if you have difficulty accessing the content, please feel free to direct message me privately today or reach out after the session, and we're happy to coordinate, if not for today, for next time. And I'll also drop a reminder in the chat about that as well. Today's slides will also be shared in the chat shortly, so give me just a minute and I'll get those out to you. You'll see both a link and a PDF version, and they are both the same files. It's just if the link doesn't work for you, which it doesn't work for everybody, please try the PDF version. We are going to be recording today's webinar, and that recording will be emailed to everyone along with your certificates, so please give us about 10 business days to process that. We'll be having a break today about midway, and you are also invited to put questions into the Q&A version on the Zoom window, which you can do anonymously, or you can put your questions right into the chat. And what I will be doing is holding those questions for later at the end of our session today. So please feel free to route those my way if you have any questions. And also, it's important, if you do need a certificate of attendance for this class, you don't need to do anything today, but tomorrow at the end of the session, I'll be putting a link to an evaluation survey, and we will ask you to complete that in order to receive your certificate of attendance. So nothing needed today, but make sure you grab that link tomorrow. Okay, so I'm going to go ahead and drop those slides in here and a couple of reminders. But until then, I will turn it over to our instructors. So please welcome Greg Pearson to get us started. Thank you, Greg. for your time, and the floor is yours.
Hello, Lori, and welcome everyone. We're glad you're here. Can you see my slides, Lori?
Yes, I can.
Okay, so you can see the map on the screen right now?
That's absolutely what I see.
Okay,
Yep.
thank you.
Mhm.
Um, wanted to tell you a little bit about what the Environmental Finance Center Network is. Uh, Michigan Tech is one of the environmental finance centers, and they're regional. And so each EPA region, there's 10 of them, has at least one EFC. We're uh, focusing on helping water and wastewater systems build capacity, technical, managerial, and financial capacity. And so we're located right here in Region 5. And, uh, and our mission is the same as the rest of the EFCs to help systems uh, in our 6 state region and in the national project to help increase capacity to produce quality drinking water and to manage utility systems and wastewater systems. Am my audio and everything coming through okay and okay to proceed further, Lori?
You sound good to me. Keep
Okay,
on
thank you
going.
very much.
Yep.
And Daryl Gotham is here with us as well. He's a senior research engineer, and he'll be providing some of the training today. And today, basically, we're going to be starting with an overview, and then we're going to talk about flushing, corrosion control, and cross connection control. Those are three elements that are going to be important to water quality. And then we're going to look at some basic water math that you'll need, and especially you'll need it for tomorrow. And tomorrow we're going to be talking about disinfection and dosage, prevention of disinfection byproducts. We'll talk about water quality monitoring throughout the distribution system, and finally, sanitary surveys. So let's jump right in here. And first of all, let's get a sense of the scope of what we're going to be talking about here. Um, the distribution system is separated from treatment at the entry point. After water treatment, it enters the distribution system at the entry point. So a lot of what we talk about for a distribution system water quality, we're talking about storage, and we're looking at things such as how old is the water? Is the storage tank clean and well managed? Is there nitrification occurring? Are there dead ends in the distribution system that can help increase disinfection byproduct formation and where we lose residual? We look at the condition of pipes and what's going on in pipes. Is there bacterial growth? Is there corrosion? Are our materials themselves causing water quality problems? And associated with that is when we have a main break or a repair, what are our procedures to ensure we have sanitary conditions that protect water quality? And then finally, we have points where contamination can enter, such as through cross connections and sanitary deficiencies. However, even though we separate treatment from distribution, there is a relationship here. We have a certain source water quality that comes into our distribution system, and that affects the quality of water in the distribution system. Also, pH and alkalinity and uh, the corrosiveness of water can be affected by different types of treatment technologies. So we'll be mentioning those types of things as they come up as they pertain to water quality in the distribution system. Uh, to give you a little bit of an overview of some of the things Daryl's going to be talking about tomorrow is water age. As water ages, it has a greater propensity to have bacteria and growth and disinfection, residual loss, and just in general, water can degrade over time. Water quality can degrade. So we want to do things such as look at the turnover in our storage tank. Turnover means how often do we get fresh water? How often is that water replaced in a storage tank? Trying to over time eliminate dead ends, but managing our dead ends by flushing and taking samples at those points. And there's been some different attempts to model water quality as it ages. And you can see the graph there has an orange line, a green line, and a blue line. That represents different water quality models. And the main idea is that as water ages in terms of hours, and you see the water quality models show that we've lost the water quality between 10 hours of age and 50 hours of age. That orange model seems a little extreme because the water quality just drops off. But the green and the blue line looks a little more realistic as you see water quality decreasing over time. And when we get to about 50 hours of water age, where water is just sitting stagnant, there's no new disinfection residual coming in, it's not moving, it's not being aerated or used, the water quality can deteriorate over time. And there's some different factors things that occur as water ages. We lose the disinfection residual. We can form disinfection byproducts. We can form biofilms, and there can be bacterial growth and things that occur with pipe scales growing and corrosion, increase in bacterial counts, which could include pathogens, increased corrosion and tuberculation, nitrification in tanks and dead ends. And you can look at this study here, enhanced water age performance assessment, and you can look at different types of water quality models that were in that study. When we look at preventing the entry of contaminants into the distribution system, there's a couple of different aspects we can look at. First of all, we can talk about cross connections. A cross connection is just a plumbing arrangement that would make it possible for some kind of non-potable substance or non-potable water to enter the drinking water supply. So it's just a plumbing connection. Nothing is necessarily happening at that plumbing connection unless there is a pressure differential that causes that substance to flow into the distribution system. There can be back siphonage where we have a loss of pressure in the system. And that can be because we have a main break, or there's a lot of fire flow, or there's some kind of outage of a pumping system or so forth that causes a lack of pressure. And then that could create the conditions for contaminants to enter. The other type of backflow is back pressure, where we have water being served, for example, to an industrial facility, and they have a pressurized tank that has chemical or non-potable water, and it exceeds the pressure of the distribution system. They might have a pressure of some kind of a pump that pressurizes their process at 100 psi, and the pressure in our system is 60 psi, and so it overcomes the pressure. Another way that contamination could enter is through sanitary deficiencies. And here we have an image of actually a well-protected air vent valve, and we have a screened inlet, so bugs and pests can't enter. And it's well vented, and it's 8 inches above the ground. So there's different things that could happen here, though. Still, let's say we had floodwaters that were 9 inches above the ground, and then that would be an entry point where uh, floodwaters, contaminants could get into the system. And a final aspect that Daryl's going to talk about tomorrow is sanitary deficiencies. And here's an example of a well casing that's not properly sealed on the top of the casing. So contaminants from flood or just dust or some kind of a spill could enter directly into the casing and down into the groundwater. There are some different things that can occur when we repair water main leaks and breaks. And in general, we want to have some procedures that help us to protect water quality. And the three basic things that we do when we go to repair a main break or a leak, or just any kind of repair to the water main, is we isolate that area by valving. We flush out the contaminants and after the repair, and we disinfect that section of main after the repair. And there's some different factors here that graph. It says table 1 at the top left of your screen is the types of things that could happen associated with the repair of water mains. One is we can have contamination by pathogens, bacteria and viruses and protozoa, and some different types of chemical issues. We could have some kind of a chemical uh, that enters. We could have a loss of uh, disinfection residual. We can have different types of problems with pH and turbidity that can enter. And they did a study here that's reflected in table 2 that they looked at break repair sites, and they sampled the water in the trenches, and they sampled the soil around the main break, and they found several instances where there was either total coliform bacteria or fecal coliform or different types of bacteria that are known to cause waterborne disease. And in several instances, they found that there was um, bacteria that would cause illness in many of the samples. So that just reinforces the need for us to, as operators, to go into repair with knowing that we're going to isolate, flush, and disinfect, and then of course take a bacterial test before we put that new pipeline or that repaired pipeline online. And there's been several instances where people have had illnesses after main breaks or repairs, or even planned repairs. And there was one that occurred that was particularly severe in 1990 in Missouri, and they had an outbreak of E. coli, and they had 240 documented cases of illness. There might have been more that we don't know about, and there was actually 4 people that died, and it was due to a couple of main breaks that occurred, and the operators did flush the pipe, but they didn't disinfect the section that was repaired, and so that led to some serious problems. And you can look at this reference at the bottom right of your screen. US EPA has a report on new and repaired mains, and that was fairly recent in 2015. And you can look at that instance, and you can see these tables and a lot of other related information. That's a good one to have in your library. Another issue that can occur in distribution systems is pathogenic organisms, and that could include bacterial, virus, or protozoa groups. And also, it can result in the development of biofilm inside of pipes. And once biofilm begins growing, it can actually protect microbes from chlorine disinfection. So they're kind of hiding beneath that uh, biofilm, and disinfectant physically can't get to them. And we're going to go to our first poll now and simply ask, how can operators protect water quality when repairing main breaks? Okay, great. I see that the majority of you said all of the above, and that is correct. Uh, Isolating the repair, flushing the line, and disinfecting the line are all uh, elements of protecting distribution system water quality. And you did that poll so fast. I'm glad we have such a great group online. And just by attending this class, that tells me that you all are interested in improving the water quality in your system, and I'm happy that you're here. And I want to mention too that this is your training. This is not for us just to talk at you. This training is for you. So as you have questions, make sure to put them in the chat. And if it's something urgent, Lori will stop us and say, "Hey, I have an urgent question you need to answer." We might not know everything there is to know, and also I will let you know that you're going to need your calculators later on in the last hour of this training. So if you have a calculator that you can reach for before then, but we'll have a little break before then too. We're going to have a break probably around maybe the hour and 10-minute point, something like that. And that what we just did was kind of an overview, kind of an introduction to the topic of distribution system water quality. And now we're going to start getting into our next topic, which is system flushing. There's lots of benefits to flushing. You can see some operators here that are making some repairs at a hydrant or preparing a hydrant to potentially add a swab or a pig in there. And you see an operator on the bottom of your screen that's actually flushing a hydrant. But there's lots of benefits. One is it reduces the water age. It can reduce the biofilms and scales inside of pipes, and it removes the sediment that collects in water mains. And it can actually help to reduce disinfection byproduct formation, and it can bring in fresh chlorine residual to dead ends. Um, Normally, we flush at least once a year. I've heard a lot of a range. I've heard of some systems flushing twice a year, and I've heard of some systems flushing every 2 years. But in general, at least annually. And when I talk about an annual flushing, I'm talking about high velocity flushing of the whole system. And but you might want to gently flush dead ends more often than that to prevent disinfection byproduct growth. And also, when you're out there flushing, it gives you a chance to put your hands on the valves and the hydrants just to make sure they're working. And you could note that if something needs some kind of repair, there's something that's malfunctioning that needs to be repaired. Even something as simple as painting the outside of the hydrant to prevent corrosion, or a valve that doesn't work, you would you would get a chance to see that. So there's a lot of benefits. In general, for flushing, we want to attain a certain water velocity. Water moves pretty slow uh, normally when we're just using the distribution to deliver water to customers. It's moving pretty slow, but when we flush, we try to get that velocity up at least to 2.5 feet per second, but ideally up to 5 feet per second. And if we can get up to 5 feet per second, that actually gives us a scouring action to remove the kinds of things that you see on the bottom here. On the left, you see some manganese that's been oxidized by chlorine and air, and it's precipitated in the pipe, and it's stuck to the outside of the pipe. When you flush that, you'll see a uh, dark brown and black water coming out of the hydrant for a few minutes, and then it'll clean up. The middle is a kind of a rusty iron slime, and on the right side is some biofilm that's been growing in the pipe. And so when you flush, you're getting the velocity high enough to remove those types of things. There's also an opportunity to use what they call pigs and swabs. Swabs are like a big foam, like a Nerf ball that goes through the pipe. It's sized to fit a certain size pipe, and so it cleans the pipe as it passes through. And pigs can be abrasive, where they have some bristles on the outside to give more cleaning action. Swab's kind of a foam projectile. Pig is more rigid and different types of abrasiveness. And you can even have specialized type of smart pigs. Those are not for cleaning necessarily, but they pass through the water main to detect things like pipe thickness, for example. Here's a very large swab being inserted into a pipeline by a couple operators. And here's some different types of pigs and swabs. You can see those white diamonds or some abrasive material on those pigs that will help to clean the line. And you can see the images from left to right. They're inserting a pig or swab into a hydrant, and then they have a connection, water connection that will push that water down to push the pig down through the hydrant into the pipeline that's flowing along, and then there's an exit point where they'll flush. They might go from hydrant to hydrant, and the pig comes out, and behind it comes the dirty water. It helps to improve flushing. Another method of flushing is ice picking, and basically what we're doing is creating kind of like a icy solution, like a snow cone solution. It's a semi-solid ice solution, and it's water and salt that's down to about 24 degrees Fahrenheit, so it lasts longer. But the big benefit, not only is it abrasive and helps to remove sediments, but it can't get stuck. A pig or a swab actually could get stuck, but an a slug of ice or an ice pig would eventually just melt. And so that's another advantage here. Um, and you can see an image here on the upper right, the ice pig moving through, and it's wiping out the sediments in the pipe. And here's an example of the samples that came out of an ice picking operation. You can see at the beginning, there's some pretty dark water that's coming out. It looks like maybe some iron slimes that were in there, maybe some biofilm, and it gradually tapered off um, as the main was cleaned. Oh, and there's an example of what the ice would look like. It's kind of like a slushy. It's produced in the truck here. It cools and creates the ice pig, and it is entered into the inlet hydrant. And there's an upstream valve here that you'll open to push that ice pig through. So the pig enters in the inlet hydrant. The upstream valve is going to push it down, and it's going to push it down to the outlet hydrant. And then normally they'll have the outlet hydrant go through a flow analysis unit so they can know when to stop, when the main has been cleaned, and they can see that the turbidity goes up quite a bit, and then it will drop off as the main is cleaned, and they can discharge uh, that dirty water to the sewer. In the analysis unit, they're also monitoring things like the pressure and water temperature, and looking at the turbidity of the water that's flowing through. Eventually, it will become clean. The turbidity will drop down to normal. When you flush hydrants, just with by opening hydrants, you can get water that's coming from different directions. If you just go and open a hydrant without operating valves, let's say we have a hydrant here at this point in 7, and we're starting from every time we start from a source of pressure or storage. We're coming from this storage tank at N1. However, between the tank and the hydrant, the water can actually travel in different directions to get down to N7, and we really don't know which direction it's going to go. So what you can end up doing is moving water around, but not, you can move dirt and sediment around, but not out. And you can have insufficient velocity. We're trying to get the velocity up between 2.5 and 5 feet per second. But if it's going different directions and coming from multiple directions, we really can't have any certainty that we can attain the right velocity. So what we use is unidirectional flushing, and what that means is we're closing some of the valves so that the water is forced to go down a certain path. And we continue to do that with each line so that we can attain the desired velocity. Let's say we're trying to attain 5 feet per second, and we use valving to do that. And like I mentioned before, going out and flushing can be a form of preventative maintenance as well, because here we are, we're operating valves, we're operating hydrants, and you could even take some hydrant flow measurements while you're at it. So this can be a really a a beneficial uh, practice to to collect the data while you're cleaning the mains. And so when we do unidirectional flushing, it's kind of like sweeping the system. So we're using a systematic method. And so the next time we might clean a different main. We might go down P3 to P4 and clean that section, or we might go from P3 to P5 and clean that section. So you want to keep track of the valves that you've shut off. Uh, it's good to have a little map where you can have something like a dry erase and put an X on the valves that you've closed, and when you open them, you can erase them, or some kind of method to keep track, because you don't want to leave a valve closed. And so you're generally working outward from the pressure source throughout the distribution system. There was a study done, the efficacy of flushing and chlorination in removing microorganisms, and you can see the study at the bottom of your screen. You can use that link. But one of the main takeaways as far as flushing is they found that the most effective and the most bang for your buck, if you will, was flushing a volume of equal to three volumes and at a velocity of 5 feet per second. That gave the most benefit. When they extended flushing as high as 15 pipe volumes, they really didn't get much extra yield out of it. It did continue to increase removal, but it was kind of diminishing returns. So you're using extra water and not getting a lot back from it. Uh, we've mentioned this a couple times, but there's some studies where you can see that main breaks and repairs are correlated with increasing waterborne illness. And some of these studies are from Europe, but there was one in Norway where they found that houses that were downstream of a main break or repair, could even be a planned repair, were 1.58 times more likely to contract some kind of gastrointestinal illness. That was pretty recent, 2007. And in Sweden, they found that people were 1.9 times more likely to report an acute uh, gastrointestinal illness after a pipe break or repair in the distribution system. And that was a pretty recent study, 2017. There's some different things we have to think about. Uh, we talked about the contaminated water in the trench or the groundwater or the soil itself. Also, if you have a main break, it can draw in contaminants through cross connections. But also another thing is that if you have sewage pipelines that are close to the same elevation or close to the area where there's a main break, that could also be a source of contamination that could enter the pipe when it's open for repair. And as we mentioned before a couple times, isolating, using sanitary repair procedures, including disinfecting tools and parts that we're going to add, and then flushing and disinfection following the repair. Those are all good ideas. And so we have a second poll here. What is a recommended flushing protocol? You guys are really fast on your polls. I appreciate that.
Okay, so we have 86% have participated in the poll so far.
Excellent. And I see that the majority of you have chosen unidirectional flushing at 5 feet per second for 3 pipe volumes, and that is indeed the recommended um, target for flushing a hydrant. Thank you for participating in that. And now we're going to talk about corrosion control a little bit. We talked about flushing. Let's talk about corrosion control. And first of all, look at the problems, what corrosion is, and some ways that we can prevent it. Corrosion, you can see a pretty poor, badly corroded pipe here. Looks like there's some real problems there. So one of the things is tuberculation, and that's when you have uh, iron tubercles that grow in the pipe where iron is being deposited, and there's an interaction there with bacteria. Also, corrosion can be involved with the release of lead and copper. We have the lead and copper rule that looks at lead and copper in customer plumbing, and that is a result of corrosion. And corrosion can also lead to main breaks and leaks. So you have not only uh, pathways for contamination to enter, but you're losing water. You're pumping and treating water, and then you lose it through cracks. And also, it can increase microbiological problems because you can see, looking at this pipe, there's lots of places for bacteria to be harbored in those tubercles in that pipe that we're looking at. In general, I'm not a chemist, but in general, what happens when a metal pipe or tank corrodes is that the iron loses electrons. The anodic site loses electrons. And here we have iron being dissolved into the water. You see that little Fe2 plus. That's an iron ion that's been dissolved into the water. And then it becomes oxidized after it leaves and deposits as a rust or a tubercle somewhere else in the pipe. And so in this case, when you have an electrochemical reaction, the pipe actually itself can have both anodic and cathodic sites where electrons are leaving the cathodic site and depositing at a cathodic site. And a lot of times these reactions will be galvanic reactions where it's between two dissimilar metals. There's a galvanic series that we can refer to here, and this doesn't list every type of metal, but the metals that are listed here go from most reactive on the bottom, magnesium, that's very reactive, to platinum at the top, gold and platinum on the top, not very reactive at all. And so these reactive metals will give up electrons. And so the electrons will flow from the more reactive metals to the less reactive metals. And so if you connect two dissimilar metals together, the more reactive metal will give up electrons and it becomes the anode. And the farther apart that metals are on the series, the greater the potential for electron flow. And here's an example here, an aluminum fitting attached to a copper pipe. And I'm going to circle the aluminum here and the copper. So what do you think is going to happen here if I connect those two? Well, the aluminum is going to give up electrons and it's going to flow to the copper. So aluminum is going to deteriorate. If we look at a copper pipe connected to a bronze fitting here, now we have the copper becoming the anode and the bronze the cathode. Now, technically, electrons could flow from the copper to the bronze, but they're so close together, it's probably not going to be a significant uh, problem here. So that's some of the concepts we can think about for galvanic corrosion. Another one here we can look at, we have a copper pipe connected to a cast iron pipe. If I go, let me just go back one here. And cast iron is down below the copper, uh, 3 below the copper. So you can see that the cast iron is going to be giving up electrons. And here's an example of just that, where we had a cast iron pipe that became severely corroded and it was connected to a copper line. Another thing that can occur is lead corrosion due to galvanic corrosion. And here's an example. We have a lead gooseneck that's actually connecting between the water main and the customer service line. And the house has copper plumbing, and the lead becomes the anodic uh, metal, and it corrodes. And then lead can enter the drinking water. To measure corrosion, we can use coupons. And here's different kinds of coupons here. We have aluminum, steel, brass, and copper. And the idea is that the coupon is the same material as the plumbing material or main material that we're trying to protect. And so we can actually have a coupon rack that contains the different types of coupons, and we can allow our drinking water flow to pass through those coupons and let the water flow for 90 to 100 days, then take them back out and weigh them and see if they've lost any weight. And so you want the coupon has to match the material that you're trying to protect. And so with any difference in weight will give us give us a reading on how severe or how much corrosion has been occurring. Also, we can protect uh, water mains and tanks by several different methods here. First of all is linings. Here on the upper right, we have cement ductile iron, cement lined ductile iron. You can see the cement in the interior. There's also an outer coating, it's black, and that provides some degree of protection as well. And those out exterior coatings on ductile iron pipe can vary quite a bit, from a simple thin paint that doesn't provide much protection to something like a material that contains something like zinc that gives a pretty good um, level of protection. And you see on the bottom of your screen, the bottom right, is some gentlemen that are placing a coating on the interior of a storage tank to protect that. Uh, they're creating a physical layer, a physical barrier between anything that would be corrosive in the water and the metal. Also, we can have cathodic protection, which we'll look at next. But here on the bottom left of your screen, you can see what they call poly wrapping. This is when they actually physically wrap a metal pipeline with polyurethane. I'm not sure if it's polyurethane exactly, but they call it poly wrapping. They wrap it with a very strong plastic to physically create a barrier between this any kind of aggressive soil and groundwater and the pipe. And cathodic protection here, we have sacrificial anodes that are going to uh, give up electrons instead of the pipe or the tank that we're trying to protect. On the left-hand side, you see a pipeline is being protected, and there's some sacrificial anodes there. They might be zinc or magnesium. And so instead of the pipe corroding, the electrons that are demanded by the corrosive conditions are going to be supplied by the sacrificial anodes. So a rectifier provides a DC current flow, and it provides the flow of the electrons to flow from those anodes continuously, reversing any kind of corrosion that would cause electrons to be drawn from the pipeline. And the same type of thing occurs on the right hand side of your screen, where it's sacrificial anodes in a storage tank. And same thing, a DC current is sent to the anodes, and electrons come from the anodes. And if there's any corrosion that's going to occur, it's going to come from the anodes and not the tank. Tank is not the anode anymore. There's a couple of concepts I want to introduce you to. The first one is the Langelier index. The Langelier saturation index, it looks at the pH at which the water is stable. So when a water is stable, it's not going to be corrosive or scale forming. And we compare that to our actual pH. So we have our actual pH minus the saturation pH If that's 0, the water is not going to be scale forming or corrosive. And the saturation pH is officially defined as the point at which the water is just barely saturated with calcium carbonate. So if you added more calcium carbonate, it wouldn't fit in. It would, it wouldn't be, you couldn't dissolve any more in the water at that particular temperature. And if you had less than the saturation level, there would be room to dissolve more. If it's negative, if our actual pH is less than the saturation pH, it means the water could be corrosive. If it's positive, it means we have a scale forming water. And if it's 0, it's not scale forming or corrosive. And so here's an example here. We have a water that has an actual pH of 6.8 and the saturation pH is 7.3. If we take the actual minus the saturation pH, we find that it's a -5. It indicates that the water could be corrosive. And of course, corrosion uh, has a lot more, there's a lot more to think about when you're trying to predict whether a water is corrosive or not. This is just one of the many ways that we can analyze the water. So if our pH is low and we're having some corrosion problems and it's due to the pH being low, we could increase the pH or increase the alkalinity. Another test or a measurement that we can use is the chloride to sulfate mass ratio. This means we look at the milligrams per liter of chloride in the drinking water and the milligrams per liter of sulfate in the drinking water. And our CSMR is the milligrams of per liter of chloride divided by the milligrams per liter of sulfate. If that is greater than 0.5, it can also be an indication that the water is corrosive. And give you an example here. We measured the chloride and the sulfate in the drinking water. There was 10 milligrams per liter of sulfate, I'm sorry, of chloride, and 22 milligrams per liter of sulfate. So if we do the chloride to sulfate mass ratio, the CSMR, we would do it simply like this: 10 milligrams per liter of chloride divided by 25 milligrams per liter of sulfate, and that gives us a 0.45. If we compare that to our standard of zero point 0.5, we would determine that this water is not likely to be corrosive. It's not corrosive because we're below. Also, we can look at the alkalinity. Alkalinity is a resistance. It's the chemicals dissolved in water that resist a change in pH. So if we have a very low alkalinity below 30, that can also mean that the water is likely to be corrosive. Any little change in the pH could cause corrosion. If we get the alkalinity to be up higher, 150 to 200 milligrams per liter, that would be an ideal situation. It would be uh, more less likely that the water could be corrosive. If we needed to add alkalinity, there's a couple different chemicals like lime or soda ash that could increase alkalinity and or pH. Another way to prevent corrosion is to feed um, a chemical that creates a protective scale on the inside of pipes, and that is orthophosphate. Now, orthophosphate may not directly be fed. We might feed phosphoric acid instead, which is a kind of a dangerous chemical to handle. We could also do some kind of an orthophosphate salt or a potassium-based salt, which are a little easier to handle. But in the end result, what we're doing is trying to create orthophosphate, which will it'll form a protective layer on the inside of a pipe, and it'll protect pipes from corrosion and also prevent things like lead from leaching out of the pipe. Like I said, phosphoric acid, it's a very low pH acid that can cause some severe burns and requires very special handling. Um, Typically, we're looking to be between about zero point 0.5 and 1.5 milligrams per liter of orthophosphate, and we don't want it to be too high because we don't want excessive scale building up in the inside of the pipe where you're losing pipe volume. Just want a thin scale that holds those like toxic metals in place and prevents corrosion. And it's shown to be effective in a variety of situations. Even when you change disinfectants, which can lead to the conditions where lead and copper get released into the water from previous scales. It's been shown to help to prevent that. Um, Phosphoric acid is H3PO4, uh, and when that is added, it actually dissociates and into orthophosphate, which is PO4. Um, and it also releases hydrogen ions, which actually can decrease the pH a little bit. And you can see on the bottom right of your screen, we had the pipe on the left didn't have any corrosion control, and the pipes on the right had a phosphate feed corrosion control program. And you can see that scale, that thin scale that was built up, and that's even a lead pipe right there that were being shown there. That's a lead pipe that was protected from corroding, and lead could not enter into the drinking water because that protective scale was there. Today we're trying to remove our lead pipes, but that shows you kind of the power of this orthophosphate. And like we said before, there's different types of salts that we can use that are a lot less hazardous, like salts or solids, and they're not as dangerous, and they don't impact the pH in the same way that phosphoric acid does, because they're not releasing hydrogen ions. The hydrogen ion is an acidic ion, and so no matter what form that we're using, the the idea is to create orthophosphate, to add orthophosphate, and that's what's going to actually coat the insides of the pipes. And so we can see a little image from EPA here, how it works. And number one, we add a corrosion control chemical. And number two, there's a chemical reaction that occurs where the orthophosphate actually binds to the metal. In this case, it's binding to the lead on the surface of the pipe. And number three, it forms a coating. And number four, it reduces the lead levels in the water. And you can see another image here of the white orthophosphate scale on the inside of an actual lead pipe. Tuberculation is a process where it involves iron bacteria, and also that process that I shared earlier where iron is dissolved, it oxidizes and then redeposits. And you can see that this causes a lot of problems. Um, it decreases um, the capacity of the pipe. It increases the friction that you have to overcome when you're pumping, and it also provides a big substrate for bacteria growth. So whether or not you're going to have tuberculation in pipes, and this would normally occur with older cast iron pipes, uh, and it's affected by the pH and alkalinity levels, temperature and the water age, and the amount of dissolved solids that are in the water, and if there's uh, iron bacteria organisms that are interacting with the pipe scale. And so as you can see, it does all these things: reduces the pipe capacity, increases the power requirements that you need to push water through the system, reduces water quality, and will result in increased breaks and leaks. There's also interactions that occur on the inside of pipes that we should be aware of. And you can see some scales here. There's a copper scale and a lead scale that are growing, some manganese oxides that are growing inside the pipeline. And when the water flow increases, these scales could be released. So if a lead scale gets released, all of a sudden you have a lot of lead that's entering the customer's plumbing. And here's again our reminder of the cathodic corrosion that can occur from lead to copper and from zinc to lead. All those types of reactions can occur, and metal is being released either into the water flow or to form a scale a little bit farther down the pipe. And what makes this condition a little bit more complex is when these scales interact with biofilms and the biofilm absorbs some of these toxic metals, they can be released at some point in the future with no warning. There's a biofilm, it will grow and then it will disperse and grow again a little bit farther down the pipe. So it creates some additional problems. So biofilms and scales can actually interact. Uh, and a good example is what we looked at a little bit earlier with the tuberculation. That's a interaction between biofilms and scales. But biofilms can create uh, chemical reactions and biological activity that occurs between the biofilm, a very thin layer of biofilm, a lot thinner than what we see in this diagram. We're not talking about inches of biofilm. We're talking about something like the thickness of a piece of Scotch tape, most likely. But between the biofilm and the pipe wall, there can be reactions that are occurring that can increase bacterial growth and corrosion. So it can also result in release of toxic metals from pipe scales, release of pathogens. We don't know when that might occur from the biofilm, and microbially enhanced corrosion. Those can all take place. And there was an experiment done, an interesting experiment here by this Belcher and Zhang, and the study was called the accumulation of lead by biofilms in water distribution systems. So what they did is they had different types of piping systems. They looked at PEX, copper, galvanized steel, and PVC. Each one of these sections of pipe had a 2-foot section of lead pipe at the beginning. So that this is simulating a customer service with a lead service line connection, or like a lead gooseneck. And then it's going into the customer plumbing. So they ran this water through it for 7 months. And what happened during that 7 months is that there was some lead from the pipe that was in the form of scale in these pipes. Then, after this 7 months, they removed the lead pipe section at the beginning. So this was simulating what would happen if you go in and remove a lead service line from a residence, and then they flowed the water for another 1.5 months. So the results were very interesting. So this was simulating flow through a home with a lead service line, and then removing the lead service line, like we're doing now in most of our systems that have lead pipe. So what they saw was they looked at the biofilms that grew in these pipes, and there was a gradual increase of lead in the biofilms in the pipes, as high as 48.39 micrograms per centimeter squared. Okay. Then they removed, at 7 months, they removed that lead section of pipe. And by disturbing that, by the disturbance of removing that lead pipe, they saw another increase in lead of about 13.45. So the lead continued to increase in the biofilm. And so they found that the lead scale particles were dislodged in the removal process and attached downstream to the biofilm. And this biofilm was containing the lead. It became a secondary source for lead contamination. So they removed the lead section, but there was still lead being held by the biofilm inside that pipe. So the biofilm scale interactions are significant. The DC lead crisis was back in 2000. And what happened was they switched from chlorine to chloramines. They were trying to comply with the disinfection byproduct rule, and chloramines produced less disinfection byproducts. When they switched, there was a scale that had built up over several years, several decades. It disturbed that scale, which contained lead, and then allowed that uh, thin layer of scale that contained lead it released into the drinking water supply, and they had levels of lead as high as 80 micrograms. And there was some homes that even showed as high as 308 micrograms per liter. Um, it exposed over 100,000 people to high lead levels. This was actually more severe than in the Flint crisis. In the Flint crisis, they switched to the Flint River, and that was a corrosive river. It had a high chloride to sulfate level, and they also were feeding ferric chloride in their treatment plant, which added to the corrosivity. And they had a similar problem, but it wasn't because of change in disinfectant. It was due to a more corrosive water, which uh, deteriorated the scale that had built up because they were using Detroit water that was using corrosion control, and this scale dissolved and allowed lead to enter the system. And they also had a CSMR, the chloride to sulfate mass ratio of 2. Remember, the limit was about zero 0.5. Over zero 0.5 is corrosive. They had 2. They also had the corrosivity in lead pipes that were consuming chlorine, so they lost chlorine residual, and it resulted in problems with disinfecting pathogens. Um, they didn't really realize the extent of the problem at first, because the sample sites didn't really accurately reflect the corrosion that was going on, because of the choice of the sample sites. And they ended up having children and adults with elevated blood levels. And the highest 90th percentile level was about 57 micrograms per liter that they measured officially. Yeah, but there was some other investigators that found higher levels than that. And you can read about this with this link here at the bottom left of your screen, evaluating water levels during the Flint water crisis. It's a very well balanced report. There's some different options we can use. We can look at the EPA decision trees in the optimal corrosion control treatment evaluation manual. And basically the options are: do we adjust pH or alkalinity? Do we feed a corrosion inhibitor? And do we instead just replace our materials? Or both. Poll 3 will give you a chance to try the chloride to sulfate mass ratio. And you have a chloride concentration of 15 milligrams per liter and a sulfate concentration of 21 milligrams per liter. And we want to know, is the water likely to be corrosive? And remember, it's a sulfide to chloride mass ratio. So the chloride to sulfide mass ratio, sorry, chloride to sulfate. You guys are doing a good job. You're a good group. I hope you're enjoying the training. And I see at least one question in the queue that we'll get to uh, in our question and answer period. Okay, I see the majority of you said the water is, yes, it's corrosive. And You did a good job here. And we'll look at the solution here. The chloride to sulfate mass ratio, 15 milligrams per liter for the sulfate and 21 milligrams per liter for the chloride. 15 divided by 21 gives us 0.71, which is higher than 0.5. And so that shows us that the water is likely to be corrosive. Lastly, we're going to look at a couple of corrosion control concepts here. And basically our goals of a cross-connection control program is we want to, first of all, we're trying to prevent harmful substance from entering the drinking water through backflow. We're identifying and eliminating cross connections and any sanitary deficiencies as well. Establishing uniform plumbing codes and inspection procedures to protect water quality. And we have requirements for installation and inspection of different types of backflow devices. And so we looked at this slide already. There's types of backflow can be a loss of system pressure that creates back siphonage or a customer pressure that exceeds the system pressure. And for a backflow to occur, we need to have a cross connection, a pathway, and then some kind of pressure differential that causes a reversal of flow through the cross connection. And of course, we looked at this example of a sanitary deficiency as well. Contaminants could also enter through a sanitary deficiency if it's not protected. An example of back siphonage could be a main break. And here we have from the EPA cross connection control manual. Here I grabbed this image here, and you have that point A. We have a submerged inlet in A. So a car runs into the hydrant. That's a wet barrel hydrant. Only wet barrel hydrants make it into the movies because they're pressurized all the time. And if you were to break that hydrant or have a main break, it would cause a negative pressure, and water could be pulled from that higher elevation tub. It could be a chemical tank or photo processing tank with toxic chemicals that get pulled. It's going past the person's sink where they're taking a drink, and it's making its way all the way in to the distribution pipe. And the kinds of things that can happen is fire flows that reduce the pressure because of high velocities, or main breaks. Sorry, I went a little faster. Or water main or hydrant breaks. Okay. So in a backflow situation like this, you have a water pressure that lost because of something like a main break. And then here's another example of something that could be a contamination source, a hose that's submerged in a chemical tank, and there's no backflow at that faucet. And then you have this reversal of flow due to a vacuum condition, and it pulls those contaminants right into the water main. On the EPA site, there's a lot of stories of backflow. Uh, and I believe in the EPA cross connection manual, there's been situations where people were taking a shower, and all of a sudden they were sprayed with lye, which sodium hydroxide, which they started having severe skin burns because something just like this happened where there was um, pure 100% strength sodium hydroxide that got drawn into the water system. Another situation was a slaughterhouse where they had some kind of drainage and a pump that would take away all the blood and body parts from the animals that were being butchered. And there was a situation where that material got pulled into the drinking water systems, and drinking water fountains around the area actually ran with blood. So I don't say that to be gross, but uh, just to let you know that these things have happened and will happen if you don't have proper cross connection control. A submerged outlet just can be a situation where you have the fill tube is at the bottom of the tank, or a hose that's submerged. Here we have some chloridane. That's a highly toxic chemical. It's now banned, I believe, but somebody's trying to fill a tank so they can do some spraying. And if there's a negative pressure and that faucet is not protected by some kind of backflow preventer, it could draw that toxic poison into the water system. So inlet pipe that's designed to enter the bottom of a tank. One time I went to a training facility. I won't mention the name, but it was a well-known uh, training organization, and they had a lab that had chlorination, and they had the city's water coming into the bottom of the chlorination tank that what that had the chlorine mix. So if there was a backflow here, this training organization that also taught backflow could have been a source of backflow. But I mentioned it to them and I said, "Hey, you can't have that water coming in straight to the bottom of the tank." I think they fixed it. So something with a submerged hose also. That's why when you have a sanitary survey, the uh, the person might mention if you have a hose hooked up, they'll say, "Hey, you can't have that hose laying there hooked to the well." A direct plumbing connection is when you have your system water directly connected to a process, such as a chemical process or a well. And some examples would be you're serving a facility that processes chemicals. They need pressure from the system, and it connects right to their process. And if there was a backflow, the chemicals could flow. That's a situation where you would need a backflow prevention device. Also, you might have a customer that also at some time had a well in their back 40. And so if they turn on that well and it's higher pressure than the um, the system, it could actually overpower the well. And here's an example of a protection situation where you have a direct connection between the water main and this chemical feeder. So that liquid in the chemical feeder could potentially make its way back out to the water main unless we have some kind of backflow protection here. And the type of backflow protection that we use depends on the degree of hazard. If you have dangerous chemicals um, or moderately dangerous chemicals, you would have a reduced pressure backflow device, and I'll show you what that is. A lower hazard might have a double check valve, and for outside customer faucets, you might have some kind of vacuum breaker. An air gap where you actually completely separate the customer's plumbing from the distribution system would be for the highest level hazards, like you're providing water to a wastewater treatment plant. Here's an example of an atmospheric breaker that you could use at a hose bib, and that how that works is it every time you turn it on, it pushes that valve you see on the top right where it says seal. That's also you see that valve moves up and it seals. It opens up as soon as you turn the water off. That that valve drops back down and it's vented to the atmosphere. Okay, so it can't backflow because it's only uh, not venting when you're using it, and as soon as you turn it off, it vents to the atmosphere. So backflow can't occur. A slightly better one is a pressure vacuum breaker, where it has a spring-loaded valve, and that means that it only is going to vent when there's some kind of a back pressure that's going to cause backflow. Otherwise, pressure is allowed to remain in the valve, and that's commonly used for sprinkler systems. So if you had a downstream pressure in your sprinkling system, it could, if you just had the atmospheric breaker, it would open it up and defeat the purpose. A double check valve provides you redundance here, and you see there's two valves in a row. It's just giving you double the protection here. And when the water is flowing, it pushes those valves open. So if you look at that top image, you can imagine the water flow would push both of those valves out of the way. And when it's closed, the water cannot flow backwards. In fact, water trying to come from upstream would force the valves close. A RPZ, or reduced pressure zone device, is basically a double check valve plus a relief valve between the two valves. So if there is a backflow, not only will the double check valves flow, but it will be vented to the atmosphere. So it's kind of like a combination of all. we've seen so far. This is used in the more hazardous situations where we need pressure from the distribution system. So both valves close and it opens to the atmosphere. An air gap here, you want to have the gap between the delivery pipe and the filling source at least twice the diameter. And there's no way that water can backflow when you have an air gap. So it completely separates the plumbing. And finally, some elements that you want to have at your local utility. You want to make sure you have some authority and some documentation of your authority to enforce the regulations. You want to know where all the potential cross connections are. You need an inventory. You need to train your personnel to know to identify backflow testing, or have a contractor that comes out and can test backflow devices. Normally, you require the customers to test their backflow devices each year and report them. You need some kind of way to keep records. And at minimum, you want to ensure that all the backflow devices are inspected at least once a year, and you want to require that you have a report submitted to the utility. And there's some resources here on this slide that you can use to access the plumbing code, International Plumbing Code, and some different standards organizations that will give you some insight into plumbing requirement. And we'll end on this last poll, and then we're going to turn it. We'll probably have a break and turn it over to Daryl. I'll let you figure out how you want to handle the break, Daryl. And this question here: which device would allow the minimum necessary protection from backflow when providing water under pressure to a chemical facility?
Hey, Lori, how about we set a timer for 10 minutes and we'll follow up with the poll after that?
Okay, that sounds good.
Can I stop share of this screen, Daryl, and you take over?
Yes, you can do that.
Okay.
And welcome back, everybody, from break. I hope you had a good one. We're going to go ahead and get started again.
All right. Thank you, Lori. So looking at the poll, which device would allow the minimum necessary protection from backflow when providing water under pressure to a chemical facility? 41% said A, reduced pressure zone assembly. 25% double check valve, 16% vacuum breaker, and 17% air gap. So let's see what we come up with. The answer is A, reduced pressure zone assembly, an RPZ. And that's most likely based off the concern level of a chemical facility. So we would want to protect that from the rest of our system. So good job, people. All right, so I'm here to talk to you about some basic distribution math concepts. So we're going to cover a few different things. We'll talk about volume. We'll talk about pressures, important concept of flow in our distribution system, concentration when it comes to things like parts per million or milligrams per liter, and how we would go about dosing some chemicals using the formulas. So the first of our volumes that we're going to be concerned with is rectangular volume. So volume is simply the length times width times height. I think most people probably know that from school. Let's see, in this case, So if our length is 4, our width is 2, and our height is 3 feet, our volume is going to be equal to 24 cubic feet. All right, so that's pretty simple stuff. One thing that's important to consider with this is, how many gallons make up a cubic foot? This is kind of surprising to me. I mean, I think of a gallon and I think of a cubic foot, and it doesn't seem like there'd be almost 7.5 gallons in there, but that's what it is. So a cubic foot is equal to 7.48 gallons. And so if we had a tank that was 24 cubic feet, how many gallons would that tank hold? So if we take our 24 cubic feet, we multiply that by 7.48 gallons per cubic foot, and we get 179.5 gallons. So I think Greg mentioned something about having calculators available. There will be a few poll questions, and they do involve math. So one thing I would, if you want to write down anything, some of these, this factor here for the weight or the number of gallons per cubic foot is an important thing, as long as, and also, just to jot down so you have them available for when you go to do the polls. That and our volume calculations, those are all important things. So if we know that a gallon is equal to 231 cubic inches, so how many cubic inches are in a foot? So we're going to convert from cubic inches into cubic feet. And the way we do that is, we multiply, in this case, we multiply our inches out just to see how many are in a cubic foot. We've got 12 inches times 12 times 12. It gives us 1,728 cubic inches in a cubic foot. All right. So then how many gallons are in that 1,728 cubic inches? And you do that conversion by taking our number of cubic inches that we had in a cubic foot, dividing that by the number of cubic inches in a gallon. And once we note that these, the inches will cancel, and that gives us 7.48 gallons in a cubic foot. So we kind of work this problem backwards, and it's important to be able to do this and with the math that we have to do with water. It's good to be able to go in different directions. All right. So we're going to move on to, we're going to start talking about volumes of cylindrical pipes and tanks, things like that. So it's important to understand what this relationship is between the 7.85 and pi. And so we all know pi is that it's an irrational number. It repeats over and over and over again, but typically when we go to use it, for most cases, we can use 3.14 to signify what pi is. All right, so pi is equal to the circumference or the area around a circle divided by the diameter of the circle. So traditionally, I know I was taught that the area of a circle is equal to pi r squared. There's been a movement to, I guess it's easier for people now to use a slightly different formula. So if we take and put, instead of the radius here, we put in the diameter divided by 2, which is what the radius is equal to, into the equation, we get the area is equal to 3.14 times the diameter, half the diameter times half the diameter. And if we manipulate our equation, we'll end up with the 3.14 divided by 4, which is the two halves, and then multiplied by diameter squared, and that'll give us the 0.785 times the diameter squared. So areas, you can use either one of these. You can use the area equals pi r squared if that's what you prefer, or you can use area is equal to 0.785 times diameter squared. And I think for most of the case in this, you'll see that we use the 0.785. And what this tells us is that the area of a circle, a circle with a certain diameter and a square with the same sides, the area of the circle is 78.5% of the area of the square with those same. If the diameter is the same as the width of or length of the square side, you're going to have 78.5% of that area is the circle. Square equals d squared, circle is 0.785 d squared. And that works out to roughly a quarter. So cylindrical volume. So we did volume of a rectangular prism, and now we're going to look at cylindrical volume. And it's simply that the area, the 0.785 times the diameter, and then we multiply that by the height of it. So we're going to determine the area at the end and multiply by the height, and that'll give us the volume. Okay, and if you're one who likes to use pi r squared for your volume, you can just multiply that by 8, the height, and that'll also give you the volume. So let's look at a little problem here. What is the volume of a tank with a diameter of 20 feet? So your diameter is 20 feet and your height is 30 feet. So we've put that into our equation. And if you're doing it at home on your calculators or at work, it's 9,420 cubic feet. So if we want to determine how many gallons there are in there, and we know that how many cubic feet there are, we can multiply our cubic feet by 7.48 gallons per cubic foot. The cubic feet will cancel out, and it's going to give us a number in gallons. So that works out to 70,461.6 gallons. That's equivalent to 9,420 cubic feet. Okay, so we've got our first bowl here. A cylindrical storage tank with a diameter of 24 feet is filled to a height of 20 feet. How many gallons are in the tank? Lori, could you set us up? We'll just give 3 minutes for this one.
Timer set.
Thank you. Okay, so it looks like our 3 minutes are up. So we'll end the poll, and so it appears if the favored answer at 80% was C. So let's go over how we come up with our answers. All right, so a cylindrical storage tank with a diameter of 24 feet is filled to a height of 20 feet. How many gallons are in the tank? We take our formula for determining the volume of the tank, and we multiply that by our 7.48 gallons per cubic feet. 24 times 24 times 20 times 7.48. Our cubic feet cancel out. So that's an important thing to make sure that we're getting rid of our units there. So our answer is in what we need it to be in. And the answer is 67,643 gallons, which does equate to answer C. Great. So let's talk about flow. That's our next concept. So flow is important for distribution systems. Obviously, we want that water to flow through our system, and flow is equal to the area in our pipe times the velocity that water's going through. And units for flow are typically in cubic feet per second, or CFS. The area of the pipe we most often work in is in square feet, and our velocity is often in feet per second. We'll see later that these things can change, but to start this discussion, we'll use those units. All right, the area of the circle, as we said before, 0.785 d squared, or pi r squared. What is the area of a circle with a diameter of 4 feet? We've done problems like this already. Area, in that case, of a circle with a diameter of 4 feet is 12.56 square feet. So let's throw in some velocity into this equation. Water is moving through a 6-inch pipe at a velocity of 2 feet per second. What is the flow in CFS? So the first thing you would do is you'd convert from inches to feet. So we have consistent units, and we want CFS, it uses feet. So 6 inches divided by 12 inches to get rid of the inches gives us 5 feet, or 0.5 feet, so half a foot. I think most people probably knew that was the answer. Next, we would go through and we'd calculate the area. We put that 0.5 feet into our area formula, and that gives us 0.19625 square feet. So now we've got our area, and we know that flow is equal to area times velocity. Okay, they gave us the velocity at 2 feet per second, so we have everything that we need. We just need to put that into our flow formula. So if we put those numbers in, once again, we have feet squared times feet. So that's going to give us cubic feet per second, or it works out to 0.3925 cubic feet per second, or CFS. So if you've got a 6-inch pipe with a velocity of 2 feet per second, our flow is about 0.4 of a cubic foot per second. So now we're going to look at it a little different. Sometimes you go to figure this stuff out, and maybe you know the flow and you know the area, but you need to solve for what is the velocity. So if we take our initial formula where flow equals area times velocity, we divide both sides of the equation by the area. What that does is that removes the area from the velocity side of the equation and puts it on the flow side. And so they cancel that area cancels out on the right side of our equation. And in essence, it gives us our velocity is equal to our flow divided by our area. So now if they give us flow and they give us area, we can determine what our velocity is. So a pipe with a cross-sectional area of 0.23 square feet, so they're already giving us the area, they didn't make us calculate that, has a flow of 0.75 cubic feet per second. What is the velocity in the pipe? So we know that our area here, and we've got our flow here. So we just put those into our equation. And so velocity is equal to 0.75 cubic feet per second divided by 0.23 square feet. In this case, we're going to cancel all but the 1 foot on the top, the one unit of feet on the top, and we'll have something in feet per second. It's 3.26 feet per second. So as I said, we've got we'll have some poles, these formulas, the flow formula, the velocity flow formula. Those are probably important things to maybe jot down that might help you get through the pole questions. So flow rate can also be denoted in gallons per minute. So we'll look at a little scenario here where we've got a pump filling a 5,000 gallon tank, and it takes 12 minutes to fill that. So they've given us the volume of the tank and they've given us time. So what is the output in GPM? So we know that it's 5,000 gallons and it takes 12 minutes to fill it. So we can simply divide the gallons by the minutes and it gives us gallons per minute, or GPM. So that's 416.7 gallons per minute. So now you get that same pump. And we know that it pumps 416.7 gallons per minute. How much would it pump in an entire day? So when I work one of these problems, what I like to do is I like to take it step by step so that I know that I'm going from gallons per minute today. The first thing I know to get rid of minutes is that there's 60 minutes in an hour. And if I want to get rid of my hours and get to days, I know there's 24 hours in a day. So that's how I write them out. The minutes cancel because we've got a minute on the bottom, we've got a minute on the top. The hours cancel for the same reason. So it's simply taking our 416.7 gallons multiplied by 60 by 24. We'll be left in gallons per day. We multiply those all out and we get 600,048 gallons per day. So a pump of a 416.7 gallon per minute pump is going to pump over 600,000 gallons in a day. So this is just a handy little thing. If you want to know, if you like just doing the conversion rate from minutes to days or minutes to hours, or however you want to do it, you can do this minutes to day conversion by just taking, there's 24 hours in a day, there's 60 minutes an hour. Your hours are going to cancel out, and that's going to give you 1,440 minutes per day. So if you're good at memorizing stuff, you can do that, or if you're not so good, you can do it like I do. So you will have need at times to determine from gallons per minute how many million gallons a day there is. So if we look at we've got our gallons per minute, we multiply by 1440 minutes per day. And if we divide that by a million gallons, and this is per a million gallons. So this is basically like dividing it by 1. We can take a pump that produces 400 gallons per minute. That goes in, that replaces this. And we know that there's 1,440 minutes in a day. Our gallons will cancel, minutes will cancel, and we'll end up with 0.576 million gallons per day. So that's how we would go about converting from gallons per day to million gallons a day. Flow rate conversions. So we can convert between cubic feet per second and gallons per minute. So if we've got our cubic feet per second, We multiply that by 60 seconds per minute. And then we multiply that by our 7.48 gallons per cubic foot. That's how we can go through and convert from cubic feet per second to gallons per minute. We can also go in the other direction. We can take our gallons per minute, multiply by minutes per second, or 1 minute, 60 seconds, multiply by 1 cubic foot per 7.48 gallons, and that'll give us in cubic feet, because our gallons cancel, our minutes cancel, and we're just left with this cubic feet per second. All right, so we have a pipe that has a flow of 0.5 cubic feet per second. What is the flow in gallons per minute? Okay, so we're going to use, we want to go from cubic feet per second to gallons per minute. We're going to use this top formula. We put, for cubic feet per second, we put in our 0.5, multiply by 60 seconds per minute, multiply by 7.48 gallons per cubic feet. Cubic feet cancel, seconds cancel, and all we're left with is a number that's in gallons per minute. We worked out, we multiply those out, and we should get 224.4 gallons per minute. Moving on, we're going to look at a pipe that has a flow of 500 gallons per minute, and we want to know what that flow is in cubic feet per second. So my initial thing is I want to get from gallons per minute to cubic feet per second. So I'm going to use this formula here, this conversion. Put in our numbers. We had 500 gallons per minute. There's 60 seconds in 1 minute. And we utilize the 7.48 gallons per cubic feet. We can just flip these over. They're equal to each other. So whether they're on the top or the bottom doesn't matter. And we need to get rid of the gallons, which was on the top of the formula to start with. So, and we need it in cubic feet per second. Hope everybody, that makes sense. So gallons cancel, minutes cancel, and we're left with cubic feet per second. And that's about 1.1 cubic feet per second. So these are important things you may want to jot down. They'd be, like I said, it could be helpful when we come to our poll question. All right, so now we're going to look at flow velocity with a conversion. So we're going to take this another step. We're going to start to put all these things together. We talked initially about volumes and areas, and we're going to try and use all these things and put them together. So we've got a pipe that has a diameter of 18 inches. It's got a flow of 800 gallons per minute. Now we want to know what the velocity is. All right, so the first thing that I would do is I would convert from inches to feet. So that we can get our consistent units. And then we utilize our area formula. It's either pi r squared or 0.785 times d squared, or times d times d. And that gives us 1.766 square feet. So we go back to our flow equation, and the flow is equal to the gallons per minute that they gave us, 800 gallons per minute. We're going to convert that from minutes to seconds by multiplying by 1 minute per 60 seconds. Our minutes will cancel. And then we're going to multiply that by 1 cubic foot per 7.48 gallons. So we get the gallons on the bottom of the equation. That'll cancel the gallons from the top on this side. Multiply that all out. We get 1.783 cubic feet per second. So that pipe that has a diameter of 18 inches and a flow of 800 gallons per minute, the velocity of the flow in that pipe is 1.783. So now we know that the flow of that is 1.783. So now if we go back to our velocity equation, which is the flow divided by the area, we put those numbers in. The flow is here, 1.783 cubic feet per second. The area is 1.766 square feet. With the units, we'll end up with feet per second. Well, when we cancel those out, it works out to 1.01 feet per second. So that's the velocity in that pipe. So we got poll question number 6. What flow in gallons per minute is needed to flush a 500-foot section of 6-inch water main at a velocity of 5 feet per second? So we'll have to put some of these concepts together. Lori, how about we give 5 minutes for this poll?
Okay.
We'll get back after that. All right, we're back. So I will end the poll. I'll share the results. So as you can see, 73% of the responses were for B, 440.4 gallons per minute. We had 14% for C and 8% for A and 4% for D. Okay, so let's see. We'll go through and we will see how to work this problem, see what the answer is. So what flow is needed to attain a velocity of 5 feet per second? You first use the area times velocity is equal to flow. So the pipe area is 0.785 times the diameter times the diameter. That equals 0.19625 square feet. So if we take the area times the volume or velocity, excuse me, we know that we need a velocity of 5 feet per second, and we have an area of 0.19625 square feet. So we multiply those two together, and that gives us a flow of 0.98125 cubic feet per second. Now we need to convert that from cubic feet per second to gallons per minute. So if we do that, to get it in minutes, we multiply that by 60 seconds per minute. And then to get it in gallons, we multiply by 7.48 gallons per cubic feet. That cancels out our cubic feet. We've got our seconds canceled out. So if we multiply the numbers together, we should have 440.4, and our units are going to be in gallons per minute, because those are the units that are left over when we do our equation, our canceling. All right, so our next topic of discussion is pressure. So pressure is the force that water exerts over a unit area. Okay, and we can express our pressure in either pounds per square inch or pounds per square foot. We also will express it in feet of water. So we know that water weighs 8.34 pounds per gallon. All right, and we had talked about there's 7.48 gallons in a cubic foot. So if we put those together, we multiply them together, and our gallons will cancel out because we've got gallons on the bottom of this and we've got gallons on the top, and that's going to give us a number that's in pounds per cubic feet. And we multiply 8.34 by 7.48, we get 62.4 pounds per cubic foot. So that's how much water weighs in cubic feet. We already knew what it weighed in gallons, right? So an example of a PSI conversion, if we have a square foot, that's equal to 12 inches times 12 inches, or 144 square inches. And we want to convert this 62.4 pounds per cubic feet because we want to know what it is in PSI. We take our 62.4 pounds per square feet. We multiply that by one square foot divided by our 144 square inches. And that gives us 0.433 PSI. So if they're the equivalent in pounds per square inch to our pounds per cubic foot is 0.433 PSI. So if 1 foot of water is 0.433 PSI, 1 PSI, we take our 1 foot, we divide it by 0.443, 1 PSI is equal to 2.31 feet. And these are typically people I mean, if you memorize one of these, either 1 foot is equal to 0.433 PSI, or that a PSI is equal to 2.31 feet, you're probably fine. Because you can manipulate the numbers as we've done to get the other one. If you can get one, you can get the other. Okay, so let's look at an example that we can do a problem that shows our pressure. So in our example, we've got a 10-foot wide by 20-foot long by 6-foot deep tank. All right, that tank we know is going to hold 8,967 gallons of water when it's full to that 6-foot level. We also know that the water weighs 74,850 pounds. And we can figure that out by taking the number of gallons that we have and multiplying it by the weight of water in pounds per gallon, which is 8.34. Okay, so that's how we get our 74,850 pounds. And we know that it acts on that 10-foot by 20-foot, the bottom area of the tank. So what is the pressure in PSI on the bottom of the tank? All right, the first step is we calculate the pressure in pounds per square foot. How do we do that? We take our 6 foot, our depth, and we multiply that by the weight of water, which we talked about earlier as 62.4 pounds per cubic foot. And that tells us that the pressure is 375 pounds for every square foot on the bottom of that tank. Now, if we want the answer ultimately to be in PSI, so we need to do a conversion. So if 1 square foot is 12 inches times 12 inches, or 144 square inches, the pressure in PSI will be, we take our 375 pounds per square foot, we multiply it by this 1 square foot per 144 square inches. So that tells us that our feet, that allows us to cancel out our square feet, and it gives us something in pounds per square inch. We divide 375 by 144, and that gives us 2.6 pounds per square inch, or 2.6 PSI. So one concept that I think is beneficial to some people is this idea that pressure is cubes of water. So we can think of that as there's cubes of water and they're stacked on top of each other, and each one of those cubes, for each square foot, each one of those cubes weighs 62.4 pounds and exerts that pressure on that 1 square foot area. So if we have 6 feet, so if we have 6 of these cubes and each one exerts 62.4 pounds per cubic foot, that's the equivalent of 375 pounds per square feet on the bottom. And once again, we've shown our conversion where we take square feet and we said that's equal to 12 inches times 12 inches, or 144 square inches. The pressure, when the pressure is in pounds per square inch, we can do a conversion and we can convert that 375 pounds per square feet into PSI. We do that, that's shown here, 375 pounds per square feet times 1 square foot for every 144 square inches. And that equals out to 2.6 PSI for that 6 feet of water. So another important thing that I had mentioned early in this was concentration, and concentration can be looked at in a few different things. We look at it as in parts per million, and parts per million is basically saying that, if we had 1 drop of something in 1 million drops, that's 1 part per a million parts. So when we're talking about, quite often we talk about substances in water, we're talking about, very minute concentrations. Part per a million parts is very few, but so that's the idea behind a part per million. Now, a part per million is equal in water terms to a milligram per liter. They're the same thing, and that's because when a milligram per liter is looking at the weight of the solids, and we're expressing them in milligrams, his weight is in milligrams, but we're looking at it in a liter sample of water. And so it happens to be that, a liter of water weighs basically 1 million milligrams. So, so we can take that weight in milligrams over the liter, and that's the same thing as parts per million. So there's a lot of confusion when people start to talk about parts per million and then talk about milligrams per liter, and they're in essence the same thing. And then simply, percent is expressing something in parts per 100 in theory. But at 1%, when we're talking about milligrams per liter, is equal to 10,000 milligrams per liter. And to check that, you could take and divide 10,000 by a million, and you should get 0.01, which is equivalent to 1%. As we've shown down here, decimal equivalent of percent is 1 over 100 and expressed as 0.01. That's kind of concentration in a nutshell. All right, so one of the more important concepts in working through math with water is the pounds formula. So the pounds formula is, we're going to take flow in million gallons a day, and we're going to multiply that by the concentration of quite often of chemicals, and multiply that then by the weight of water, or at 8.34 pounds. And that'll tell us how many, what's the feed rate in pounds per day. So to look at a problem with this, if we've got a well and it produces a flow of 600 gallons per minute, so that's our flow, and the chlorine dose is 1.5 milligrams per liter. Milligrams per liter is equal to parts per million, right? And that goes there. What is the feed rate for gas chlorine in pounds per day? Okay, so we're going to take our 600 gallons per minute, and we need to convert that into million gallons a day. So we do that, and we know that there's 1440 million minutes per day. We could also write it out, convert to minutes. We could go from minutes to hours to days if we wanted, but in this example, we're just going to jump right to that 1440 minutes per day. We know that it cancels out our minutes, and we're going to get something in gallons a day, and we divide that by 1 million gallons. And so per million gallons, so it's basically dividing by 1, but this allows us to cancel our gallons. Our million gallons is going to go on the top because it's already on the bottom here. These cancel out. We're going to be left with 0.864 million gallons a day. Now, to use the pounds formula, we need to take that the number of million gallons per day, and put it into this pounds formula. So 8.864 million gallons a day times the concentration, the dose that we were given of 1.5 milligrams per liter, multiply that by 8.34 pounds per gallon. When it's all said and done, we're going to end up with 10.8 pounds per day. So we'll go further on, and we'll look to another example of the pounds formula. A water well flows at 1.2 million gallons a day, and it has gas chlorine dosed at 2 milligrams per liter, or parts per million. What is the feed rate in pounds per day? Okay, so 1.2 million gallons a day times our concentration of 2 milligrams per liter times the weight of water gives us 20 pounds per day. If we rewrite the formula, we can look at it as 1,200,000 gallons times 2 parts of chlorine divided by the 1 million parts that was in, multiplied by the 8.34 pounds per gallon. How much does it weigh? 10,008 pounds. So 1,200,000 gallons of water weighs 10,008,000 pounds. Pretty heavy. All right, so we take that the flow that we had here, the million gallons or the pounds per day now, and we're going to multiply that by 2 parts of chlorine, and that gives us 20 pounds per day. And divide by the 1,000 parts, that gives us 20 pounds per day. This helps show the concentration in pounds formula expresses the weight of chemicals as a proportion to the weight of the water. All right, so now we have poll number 7. A groundwater well produces a flow of 350 gallons per minute. The chlorine dose is 1.3 milligrams per liter. What is the feed rate of gas chlorine in pounds per day? Lori, please give 5 minutes for this poll.
5-minute timer set.
All right, well, thank you and welcome back. It looks, if you look at the results, it looked like we have 74% of people saying C, 10% B, 9% A, and 7% D. So let's move on and see how we solve this problem. All right, so the first thing I would do is convert the flow from 2 million gallons per day. So we start with it in gallons per minute, convert from that to million gallons per day. So we do that, we multiply by the number of minutes in a day, divide by our 1 million gallons per million gallon, just to get our units squared away. And we get 0.504 million gallons a day. Our next step is we take that and we multiply that by the concentration of 1.3 milligrams per liter, our chlorine dose, times the weight of water per gallon of 8.34 pounds per gallon. And it gives us 5.46 pounds per day. All right. Well, great. So we covered today, what did we cover? We covered some, Greg did an overview of water quality. He discussed some flushing of systems, covered corrosion control, some cross-connection control concepts, and you guys bore with me through the afternoon of some basic math concepts. I appreciate that. So what are our main takeaways from this? We covered several things, but I think the main things we want to look at are flushing. Water age management is important to maintaining water quality. Corrosion control is also important, but we need to make sure that we're not causing things to get into our customers' drinking water through corrosion. And then we need to protect our water system from outside contaminants, and cross connection is one of the more important ways that we can do that. So once again, I want to thank you all for participating. If you've got something that you'd like to share in the chat, something that you enjoyed learning about today, we'd appreciate that as well. At this point, we are open for questions.
Okay, I just dropped a reminder in that please go ahead and use today's login for logging in tomorrow. It's the exact same Zoom link. Hopefully that makes things easier. And then we do have a few questions for Greg. Greg, if you're up and available for those from the previous section while we're starting off the Q&A.
Yes, I'm here.
I see you there. Okay, so the first question was from Mary. She had asked, can you take a sample from a fire hydrant to determine water quality from a well?
Well, we want to bring Daryl in on this one as well, but I'll just say initially it's for water quality from a well, it's best to have a dedicated raw water sampling tap on the well. That will allow you to evaluate if there's bacteria in the well water. And as far as compliant samples, like say you're trying to collect water quality samples from the well to look at inorganics and organics, and to meet all those contaminant group sampling requirements, and you only had a hydrant that was real near the well, I'm not sure how that would work. Daryl has been a compliance officer that has regulated systems, and I want to defer to Daryl on this one. What do you think, Daryl?
Yeah, I agree, Greg. I think that if it was something you were just kind of interested in, some basic inorganic information, and that was an easy way to get it, you could potentially use that. We as a regulator, we prefer to have as you said, a dedicated sample tap, something that, as a fire hydrant is going to be out in the system, so there's the opportunity for things to happen to that water between when it leaves your plant or your well house until it gets to that hydrant. So it's not really as indicative of the water quality that's in the well itself. Now, the basic inorganics don't probably change a lot. I mean, it it could provide some useful information if for some reason you can't get it from near, from the well, the plant tap at the well. But one of the things that I like to caution people on is that hydrants are not, especially for like bacterial testing. If you're trying to collect a bacteria, they're typically not designed to give you a good way to sample them without having the potential for some sort of contamination that's not actually in the water, but actually comes from the hydrant.
Okay, thank you both for that answer. And I just want to remind people, we do have a couple more questions, but if you have to jump off before we're done with the questions, you're welcome to. There isn't anything else that we need from you for today, other than if you're interested in the Q&A part of it. We'll see you back again here for day 2 tomorrow, same time, same link. Okay, so the next question was also from Mary, and it was, what professional would you recommend to inspect a galvanized pipe to determine what type of corrosion or some other cause?
I did a little research while we were proceeding on with the training, and there's some characteristics of galvanized pipes that I wanted to share. First of all, before 1970, galvanized pipes were dipped into kind of a naturally occurring source of zinc, and that zinc source that they used had a lot of different impurities, including some lead. So when that zinc layer deteriorates, it can actually result in some lead corrosion products. And some of the signs that you can look at yourself would, as the water operator, would be looking, is there discolored, brown colored water or metallic taste, or lower flow and pressure because the physical effects of the corrosion. And I would think that a professional plumber with some experience who's seen these types of pipes would be a sufficient professional source to analyze the pipe. And of course, there's certain types of corrosion. It could just be because there's a low pH in the water, but also there could be like grounding. Maybe somebody is grounding their house onto the metal pipes, and there's some kind of a current flow. Can you think of anything beyond that, Daryl, that would, or how would you recommend this type of pipe to be inspected?
Yeah, I mean, it's galvanized pipe is typically not used in distribution systems. So, I mean, we're probably looking at more residential use. My experience is that it's not a very good product. For all the reasons that Greg has mentioned, there's a lot of downsides to galvanized, and it's so, I mean, as far as inspection, I mean, my experience is that, typically if you have the opportunity to replace it, it's better to replace it than it is to, inspect it.
Okay, thank you guys for that answer. The next question was from Beth. What are others' experience with the effectiveness of poly-wrapping ductile iron pipe during construction?
The answer to that is it has a long history of effectiveness. And I'm going to share a link for you here. It's the Ductile Iron Pipe Organization, and they talk about it here. But whoops, I just sent that to Lori. Sorry. Let me send it to everyone here. Let me try that again. And it's been proven over the last 50 years as a very effective method. It's low cost too.
You said low cost?
Low cost.
Low cost. Okay. Thank you for that. Sorry, I didn't mean to talk over you. And then we have one more question. This is from Matthew. Thinking about corrosion control and scaling, what are the hazards for homeowners who use point of use water softening, hardening when their source is treated with chloramines?
I saw you nod your head, Daryl. You have, go ahead.
Well, no, I just, I mean, as far as specifically with chloramines, I just know that that is a concern that you know, as somebody from the regulatory world, you know, we never wanted to see a lead copper site being somebody that used softeners, you know, they were excluded because they're affecting you're looking at as a system-wide, you know, is this a system-wide issue, but that's a specific to a residence or a homeowner. So that's why I was nodding my head, is because I could see, you know, it does become problematic when, you know, when you're trying to apply the lead copper rule to homes that have their own softeners.
That's interesting. So you wouldn't even consider that to be a valid sampling point because it wouldn't represent the quality of the water.
No, and it's like the homeowners doing their own treatment.
I also saw some evidence that chloramines can be more corrosive to copper pipe, and a lot of that is from vendors that want to sell you a whole house filtering system. But there does seem to be some evidence that chloramines cause greater corrosion of copper, and it depends on if the term that was used was point of use. So if it was truly point of use with like one faucet, it would just be like one section of the plumbing. But a lot of softeners are a whole house.
Mhm.
So if you're softening, you're removing the hardness, and the chemicals that would normally coat the inside of the pipe are gone, and the alkalinity is lower. There's greater uh, potential for corrosion, plus the chloramines. So for copper pipe, it would probably be uh, somewhat of a concern to at least to watch out for, and changing material from copper to like PEX or something like that would help. And you could filter, if you were trying to get rid of just the chloramines, you could filter that with a carbon filter. But then again, once you remove the chlorine or the chloramine, you know, there's past that filter, there's going to be no more disinfecting power. So those are some things to think through if you have that situation.
Very good. Thank you both. And that's what we have for questions currently off the list of questions received over the entire session. If anybody has any questions that they want to throw out there for right now, we will sort of sit tight and stay here for another couple minutes if you have something on your mind. Otherwise, you're also welcome to let us know your questions tomorrow, and we will loop them in at the end of tomorrow. But in the meantime, thank you guys for the great information today. Thank you, Ingrid, for the producing and keeping us all up and running still on the back end side there. And if anybody has anything that they would like us to answer, please go ahead and throw that in the chat. We'll stay here for another couple minutes.